legal purposes has replaced almost the last model stored in this famous science museum in Sèvres next to Paris, which was supposed to be the unit of a mass. The Kibble scale is the mechanical and electronic device which replaced the unit of a mass. And what it actually measures, it measures with the accuracy to the 10 to the minus 34 of one of the fundamental constants of nature, which is the Planck constant. And what you see now on the screen is the Planck constant. Pay attention that this is a Planck constant not divided by 2 pi. It is just h, not h bar. And the 2 last red digits are those which are not so far measured with accuracy better than 10 to the minus 34. And if you look at this machine, you have the impression that it by itself is a piece of art. It is incredibly beautiful piece of machine tooling. And perhaps a glimpse on that device allows you to already understand that what I will be trying to aim at is to show that there is no really difference between a science and culture or art or whatever. But if you are not impressed by the real machine, which makes that almost all the units in which we measure physical phenomena in our world are now replaced by the fundamental constants of nature, like a Planck constants, electric charge, and velocity of light, then if you don't think this is sufficient to convince you that this is a piece of art, let me show you the same device, which was manufactured by the same group of scientists who made the balance on the left at the NIST. This is the Kibble-Watt balance built up from the Lego bricks. The Lego bricks used in this construction are purchases in a store, Lego bricks, and the only other items contained in that constructions are the electronic chips, which have to be purchased from the producer because they cannot be assembled out of the pieces of plastic like the Lego bricks. So that is also something, I mean, of course, because of the mechanical accuracy of a Lego bricks, which is fantastic by itself, is far from mechanical tooling available in the laboratory of NIST. The accuracy of the Kibble-Watt scale on the left and the right are completely different. But anyway, these are the examples of the science and art simultaneously. And perhaps we shall see that there are just much more interrelation between the science and culture in the course of our meetings. Let me show you a few more examples. For example, this is a table of values of a Planck constant, which I just have generated from the results obtained from the because of this this labeled in red color digits are not sufficient, can be arbitrary with the accuracy of the experiment. I generated a certain number of those possible values of a Planck constant within the accuracy measured by the kilowatt scale, and I put them on a plane. And if you will never be told that this is a Planck constant, you will all over a sudden see a canvas. If I will generate a big piece of cloth covered with those numbers, you will see the canvas covered with those digits. And what you see below is a painting by a very famous Polish painter, Roman Opałko, and who had made lots of considerable size even paintings, which are essentially only covered with the sum distribution of digits. By the way, if you will be having a free time and took a walk over the Bobrowiecka Street in Warsaw, that is next to the river, then you can enter. I hope it's now open after the pandemic. Restrictions are being slightly lifted. You can enter the hall of the main building of the Polpharma Consortium and visit the Museum of Art of the Staraks family, which is in there. And they have essentially, I believe, all paintings of Roman Opałko in that form on the exhibit there, plus, of course, the other paintings. So this is another example that you can be so fascinating with the numbers as to try to convey a certain feelings to the viewers, like Mr. Opałko had did with the not so complicated numbers like a Planck constant, but just by the simple digits. So now a little bit more serious problem. What you see here is one of the most impressive paintings the mankind has so far created. It's called the Starry Night, and that is a painting by Vincent van Gogh. What you see on that picture is the imagination on the canvas made by Van Gogh of something, as he described in a letter to his brother, he has seen through the window of his room in the mental asylum to which he was confined after the mutilation of his ear. What you see on it is a landscape and a strange behavior of a light coming from a left, which forms the vortices, like the light. I'm almost sure that none of us has ever had that impression by looking on the Starry Night. But somehow Van Gogh have seen the phenomenon happening to light, which is a very common phenomenon in the other areas of the surrounding us world. What you see here is a, a strait of vortices, which hydrodynamicians call the von Karman vortex sheet, street, which is the picture, a photography of clouds generated by the wind blowing from a Pacific Ocean toward Mojave Desert. And as you see, we see these vortices being created. These are vortices in a cloud, not the vortices of the light. This is a picture made in the laboratory of the von Karman vortex streets, and you can easily see that they look like what was on the Van Gogh picture. On the left side of that photography, there is a stream of liquid coming to a blunt object, which is that black, more than the rest of the picture region here. And then we see these vortices being created. I'm sure most of you have seen those vortices during the vacations, because if you take the boat and the paddle boat and you move the paddle in the water, then you leave these kind of strait of vortices behind the boat when you push the paddles. And that is a hydrodynamic phenomenon, which we can easily describe in mathematics. I'm just showing you one of the papers I happen to have on my desk about the vortex structures around the flat paddle impeller for stirred vessels. What you see here is a computer generation, and what you see here are the traces of a dye in the liquid perturbed by the paddle, and they look exactly like the light vortices in the picture generated by Van Gogh. These vortices are important also in the other part of science and also art, which is the architecture. And what you see here is a picture of Burj Khalifa, this incredibly tall building ejected in Dubai. And there are clouds, but in the wind which blows towards this building. And as you see, there are no vortices. This is because the architects who knows that these vortices created by a stream of air or liquid attacking with a considerable velocity a blunt object exerts a strange force on that building, on that construction. And therefore, in order to avoid that, you have to do something with the surface of the object, make it rough. Then the roughness of that surface destroyed the creation of the von Karman vortices. And that is why this Burj Khalifa is, as you see from the picture, not just a tall building, but it has this structure in its outer shell. A few days ago, I have read in New York Times the story about the tallest apartment building in the world, which has been built in New York, and which is just a glassy slab. It doesn't have any structure on it. It's just extremely tall. I don't remember exactly how there are more than a few hundred floors there. And this building is having a tremendous problems for the people who bought the apartments there. The cheapest one was something like $30 million. And the building is shaking so violently, essentially all the day, that the internal structure of the building, all those pipes, channels, wires, and so forth, are not standing. They are breaking in, and there are crews of people running all over those floors, fixing that building. And that is because of the fact that the air passing around that building generates the von Karman vortices, and the force by them on the building creates the unpredicted by architects results. So somehow Van Gogh predicted that the same kind of phenomena as we observe in the macroscopic world may happen to the light. We know that the light is just the electromagnetic wave. So the question, can we generate the vortices in the electromagnetic waves, in the light somehow? Well, we are not able to do that in the laboratory so far, but what I'm showing you here is a picture from a paper written by a founding father of a Center for Theoretical Physics and his associates, Professor Iwo Białyszyński-Birula, in which they have proven that there is a possibility of creating the electromagnetic waves which will form the patterns which you see on the left side of that transparency. They are nuts. They are like vortices. And the only question so far is that, at least as far as I know, there is no experimental idea how that can be created. As far as I understand, most of the researchers working on that field were always thinking about generating those patterns by a properly tailored antennas. But nobody thought about creating them by a diffraction. And the diffraction of a light, the fraction of electromagnetic wave, will be something similar to the creation of the Karman vortices by the paddle or by a wind blowing around the objects. So as you see, the artist in the one particular picture, by a strike of genius, might create the problem for a scientist, which the scientist should solve in the near future. All right, so now I was about to talk about what is science and what is art. That is a statement attributed to the Paul Gauguin. This is an autoportrait of a Paul Gauguin, one of the pre-impressionists and impressionists. And there is this sentence: there are two kinds of art, revolutionary and secondary, plagiarized. The revolutionary art is, in the Gauguin sense, it's the art which tries to break the rules of existence and tries to invent a new technique and new methods to convey a that information which the artist wants to convey to the audience watching that picture or watching the movie or reading the book. This is the revolutionary in the sense of Gauguin. And all the rest is secondary, and some of them is simply a plagiarized piece of art. So that's the definition of the art by Paul Gauguin. And what I will show you now is essentially the same kind of a description of a science given by one of the greatest scientists of the 20th century, Lev Landau. And I was not able to find out any painting, a picture, an auto-portrait of Landau. So I found that nice stamp, which is the stamp of Azerbaijan Post. I have the foggiest idea why in 2008, the Azerbaijan Post decided that it was 100 years of Landau, but why? Well, anyway, this is the Lev Landau. And what you can read on the right side is this famous statement of Landau. There are two types of physics, new and linguistic. Linguistic in the Landau vocabulary was a description of something which is the same as, if I can go back, as what Gauguin called secondary. The news physics, the science and physics is divided in these two areas. A new one, which tries to answer the new questions, and linguistic, which is whatever is else. And I think if you read those two definitions of what is art and what is science by these two geniuses in their own, so to say, field, then you can easily conclude that these are basically the same statement. So now we can go and start talking in more details on art and science and art and culture. And I shall start with the discussion of the paintings. What you see here is a painting of a Gérard David from circa 1520, which the painting resides in Metropolitan Museum in New York. And this on this picture, I mean, this is a problem of the computer screens that, but what is remarkable with that picture is that you can easily, I mean, if you look at this, you easily can see in what point in space, three-dimensional space, is the Gabriel located. So that allow me to give you the following definition of what is the painting. The painting is this illusion of a three-dimensional world. This is the room and the Archangel Gabriel, which is illusion of a three-dimensional world on a two-dimensional world on the flat canvas. This is a painting. So we have some cloth surface. This is completely two-dimensional. And the other feature of a painting is that it is having a material structure which is specific for that particular painting. For example, this, as I said, is a painting on a canvas. Let me show you another example. This is a picture by Alexander Archipenko, which is in the Los Angeles County Museum. And that is from, I believe it's the beginning of the last century painting. And it is interesting because it, in a certain sense, violates the two rules which I just have introduced. Namely, it is not projection on a two-dimensional world entirely, because the material structure of that is different from a pure canvas just covered with some paint. These pieces are actually projecting out from the surface pieces of wood and leather, which have been used by the artist to create the impression in whatever he wanted for us to understand from that picture. So the painting, the piece of art might not be always an illusion of that's why in that view graph, the dimensions are written in the red color, that are illusion of a three-dimensional world painted on projected on a two-dimensional world. And in the 19th century, after this remarkable short habilitation paper by Bernard Riemann on the foundations of a geometry, which open up the gate to the non-Euclidean geometries, and which launched the interest of us, the humans, in the possibilities of geometries which are higher than three-dimensional. There were artists, and there are artists, who wants to create the illusion of a more than three-dimensional objects, for example, four-dimensional objects, on a two-dimensional planes, the pictures, or even in a three-dimensional space, which is the space surrounding us. We will be talking a lot about this part of art in what follows, but let me just tell you, let me do a little bit of advertising of this further part of the talk. You all have seen the picture, the painting with which the direction of art, which is called the Cubism, started. These are Mademoiselles of Avignon by Pablo Picasso. When you now close your eyes and try to see that picture, you might observe that there is one of those mademoiselles, which is called kneeling mademoiselle, and her face is actually almost a copy of a drawing by a mathematician and engineer from the end of 19th century, who had written a book about the projections of a four-dimensional objects on a two-dimensional plane. And the cubism, the painting a cubism, is the part of science which is part of art, which is closely related to the attempts to use the illusion of a higher dimensional world, either on the paintings like the cubit, like a Pablo Picasso painting. But if you will go to Paris and took a subway to the Défense and see that giant new Arc of Triomphe, which is in there, then you will be looking at the one of possible projections on a three-dimensional world, on a four-dimensional cube called tesseract, which is a mathematical invention of a mathematician and engineer. About him we will also be talking in our further lectures. So that illusion by the artist, which for a long time was the illusion of a three-dimensional world on a two-dimensional world, is now not truly correct, because we already have we can see them, the projections of a higher dimension objects on the two-dimension and three-dimension world. All right. So what is this? I said that it also depends on the material structure of the particular paintings, because like the David, who used just the canvas, or Archipenko, who used this corrugated surface to create the impressions. So what is that material structure of the painting? I have listed in that slide a certain basic ingredients of the painting. Well, the first is just the paint, the colors on the painting. This is called pigment. And that is just a granular medium, which is organic and inorganic, which is used to create the impression of a colors. What that means, we will be also discussing at our meetings. The pigment is mixed up with what is called the binder. It's an organic, the lots of that bindings. Some material which keeps these granular pieces of a pigment together. And that might be the organic eggs, a rubber or oils, or there are, of course, synthetic polymer acrylic binders nowadays. And that is just something which keeps the pigment pieces together. There is also compatible with the binder substance, which is usually a liquid, which makes that binder and pigment together, and which allows me to distribute it more or less evenly, or depending on whether I want it, even on the surface or on the what we will be discuss in a second. That is on which the pigment with the binder and vehicle is being put on is called the support. And there are many possible support. There are linen canvases, there are walls. We have just a few years ago have finally seen the Last Supper of Leonardo da Vinci, which is a painting on a wall, which has been saved for the future generations. The support may be a piece of wood, maybe also a glass. The glass is a particularly versatile material for a support because it can be used and by its refraction properties can be used to generate various effects, visual effects, which cannot be generated easily for example, on a canvas. Then there is something which is called the size. That is the material, which is mostly glue, which is used to prevent the paint binders and all the others to interact too strongly with the support. If we put up this support, these are chemical compounds. So they might chemically react with the materials out of which the support is made. And if we want to prevent that from having unusual consequences, like a painting fading away in the time or something, or changing colors, or dissolving itself over the surface of the support, then we have to use the size which prevents it. And the final is a ground. This is called gesso in the Italian. And this is usually animal glue or a chalk or a white pigment. That is what it is covered directly on the support, and to make it, so to say, even, to make the surface of a support, if it's plain, to be completely flat, and then these other items can be put on it. So we have more or less something, and that is how it looks like. We have a canvas, which is the support on the bottom, and there is a ground, and this top layer is the layer of a pigment and these other items, and their picture is, for our eyes, is the incident light which comes and it's deflected by a structure of the pigment layers and so forth, and then is being reflected from that picture. So as you see, the artist must be very skillful by his knowledge of physics or his talent to adjust those layers such that the laws of optics, diffraction of the lights and scattering, will not distort or will be used to create that image he wants us to see. What you see here is a famous fresco painting by Diego Rivera, which is called The Fascination. I think I use that particular one in order to, because I think it's a proper time to include the pro-vaccination propaganda in every possible place. That is the painting. This is a wall painting in the Detroit industry from 1932. And it's a colored fresco. And this is the ultraviolet microscope picture showing you how the layers of a pigment and everything else looks like in the direction vertical to the wall. This dark, very dark layer on top of it here is actually a greenish part of it. It's from here, I believe, which is the pigment. There is a compound which contains a chromium, and what is below is a layer of a carbon dioxide saturated object. And that is actually how it is, how it looks like on the drawing. We have a wall, that is the wall, and here is the air, ambient air, and the water. Well, I should say that the frescoes are painted on the wall. So the surface on which the picture is built is a wall. And it is painted on a wet wall with all these other items being also slightly wet. And the process of drying makes the painting actually interacting with the wall. So that is, I said that there are substances used to prevent the chemical reaction between the pigments and base and whatever with the canvas or wood or something, but the fresco is essentially using this interaction, and it is using it by drying, by changing concentration of a water in the layer. The water is going from a plaster into the wall, and it's also evaporating. So the concentration of a vapor is changing, and the carbon dioxide from surrounding air is diffusing or going over through the layers of a paint into the wall, and that makes these two the structure which you can see on this ultraviolet light picture. So the physical construction of the painting is extremely important from the results obtained by the artist, and we can investigate that nowadays not only by just looking at those pictures, but by using the normal microscope, ultraviolet microscope, and we will be talking slightly about that when we will be talking about the faking of the art. But for example, the ion beam accelerators can be used to illuminate the surface of the painting with the beam of ions, which interacting with the matter on the painting creates the X-rays. And since the X-rays can allow us to identify the elements which are particular elements in the paint and pigment and so forth, we can easily, for example, find out that if the spectrum of X-rays emitted after the illumination by the ion beam comes from the elements which were unknown in the 16th century, then we can easily say that this picture is faked. We will be talking about it slightly later. All right, now about the pigments, because the pigments are those which makes the colors. And there are various possible pigments, and the optical properties are basically of three kinds. They are absorbing, metallic, and interference. And I have made a slide pictures what is absorbing. It's the light beam comes to the pigment, and it's being some part of it, some colors of the white light coming to the painted surface is absorbed, and therefore we see a certain colors. The metallic ones are that the light, which is electromagnetic wave, comes to the surface, to the piece of metal, and scatters from it. But we know that the electromagnetic wave can penetrate into volume of a metal, and the depth on which it can penetrate depends on the number of free electrons in the given metal. And that gives a color of a metal. The color of the metal depends on how many free electrons are in the given metal. And the cutoff frequency of light, or a cutoff length, penetration length of an electromagnetic radiation inside of the metal depends on a characteristic frequency, which is roughly speaking a plasma frequency for a given concentration of a free electrons, which is a square root of the, basically scales like a square root of the number of electrons. And there is interference, which is shown on the last picture. And that is, of course, that the light, when it comes to the material like a glass, then it scatters, and it scatters depending on the refraction index of that material. And if we make a glass which has a different refraction materials depending on the depth of the thickness, for example, of a glass, is, excuse me, then we can achieve various visual effects. This is an example of a metallic pigment where the colors depend on the thickness of the layer, and this is a layer of a titanium dioxide. This is the reason why I have chosen this particular substance, is that this is the this is the white paint. It is common white paint used by the farmers to paint the walls of the shacks in the from prehistorical times, and it has a not only optical properties but also it has a certain, the substance is biologically active. It is this titanium dioxide is used in the contemporary materials which are used to cover various objects in order to prevent them from being areas on which the bacteria or viruses can gather or form in the concentration which might be harmful for us. There is a company which uses basically titanium dioxide compound to prevent the items which lots of people touch from being a health hazard to them. And for example, we had hired one of those companies to cover all the exhibits at the Copernicus Science Center with the layer, so you can safely touch anything in the Copernicus. All the exhibits, they are not dangerous. They are not being covered with the SARS-2 viruses and other microbes, etc. And the thickness of a titanium dioxide layer is such that when it increases, it changes the color, which you can see. And let me now go over to next part, which is important, namely how the light is related to color. What does it actually mean that we have seen a given color created by an artist by using a combination of pigments and so forth? And I'm sorry, I just realized I forgot to put the name of this gentleman on the picture. This is, of course, Max Planck. The Max Planck, who was a 19th century very conservative scientist, who nevertheless had created the largest so far revolution in science, exactly in 1900, when he published his paper in which he explained the properties of a black body radiation by introducing a concept of energy quanta. The Max Planck, a father of the quantum mechanics, had explained the properties of an electromagnetic radiation emitted by a black body. And what you see on that picture is the drawing you must have seen hundreds of times. It's the intensity of the light on the vertical axis plotted as a function of the wavelength of a light on the x-axis. And the black curve here is a classical theory, which had not explained what is experimentally observed. And these are the curves of which have been derived by Max Planck. And that is the energy as a function of a wavelength. And as you see, it contains the Planck constant. And the important part of that formula is this exponent. And what is there is a Planck constant, velocity of light, wavelength, a Boltzmann constant, which is a physical, which is a coefficient converting the units of a temperature to the units of energy, and T is the absolute temperature. And the visible light, the light which we are interested in watching the paintings, is the light of a wavelength, roughly speaking, between 380 and 780 nanometers, and a nanometer is a 10⁻⁹ of a meter. So that is that region on the picture, that vertical rectangle. And as you see, in that function, there is a product of a wavelength and the temperature. And that determines the maximum of that curve. And one of the consequences of a Planck formula, and actually something which was experimentally concluded by research, by experimental physicists before the derivation of a Planck formula, was that there is a relation between the maximum of that curve as a function of the wavelength of a maximum of that curve and the temperature. And the product of a temperature, absolute temperature, and the wavelength which corresponds to the maximum to that curve turns out to be constant. This is a Wien law. And that is, of course, why in various areas of engineering and art, the colors are described by a temperature. Because once we know the maximum wavelength of a given color corresponding to the temperature, then it is the same whether we write here a temperature or the maximum wavelength, because the product is constant. So this is why if you are adjusting the color screen of your computer, then often you are allowed to, the language used for that is a temperature. That there are some colors which are warmer and some colors which are colder. Well, the red color is 3000 Kelvin and the blue one is a 5000 Kelvin. And that relation between the color and wavelength is given by that property of a Max Planck curve. By the way, I said at the very beginning, and we started our talk by looking at the Kibble-Watt balance, and I said that this is something which replaces this Sever model of a kilogram. And I said that most of our physical units nowadays are expressed by these fundamental constants of nature. And unfortunately, this is not the case with the scale of the temperatures. The people at the Bureau of Standards have tried for years to build up a model of a 1 degree Kelvin, which will be based on the fundamental units of nature. The idea was very simple. If you have the ideal gas, like argon, for example, which is at the very low density, then this gas is an extremely good model for what in the course of statistical physics or thermodynamics is called the ideal gas. So its equation of state is extremely simple. A product of a pressure times is equal to the density times a temperature, and there is some constant, which is gas constants, which is basically the Boltzmann constants Kb times the number of moles or whatever. So so that means that the sound velocity in the ideal gas is a simple function of a temperature. So if we will be able to excite a spherical sound wave in the ideal gas, I will explain in a second why spherical, then by measure the frequency of that sound, we will be able to measure a temperature of it. And since we can measure the frequency using quotation mark fundamental laws of nature, we can measure the frequency with fantastic accuracy by many experimental tools, that would allow us to relate the unit of a Kelvin to the frequency and therefore to the fundamental units, fundamental constants of nature. Well, how do we excite the spherical sound waves? Well, it's very simple. We make a spherical cavity and we put up a transducer in the middle, and we create what in the quantum mechanics we will call the S wave, the radial vibration. Why radial? Because if there is a radial vibration, then the residual viscosity of that gas is of no importance. And the bulk viscosity of the ideal gas is essentially zero. So the question is, we can do everything in that experiment except of being able to make a spherical cavity. And there is just no way to make a spherical cavity with such a sphericity that it will compare with the classical unit of Kelvin, which is given by a device called the gas thermometer. And by the way, it is also in the Bureau of Standards, or NIST, in Gaithersburg, where a several floor underground, there is a giant gas thermometer, which is used to calibrate the temperature. If you want to get there, I had this fortune that for years I was closely associated with the particularly statistical and thermodynamics group at NIST. So I was taken for a tour of it. You have to put on a certain uniform, which is basically like a cosmonaut uniform, and you have to go down in several stops to this very deep in the earth storage place where the thermometer is, because you have to thermalize your uniform with the surrounding world, and in order not to disturb the proper temperature in that storage place. So that is a physical relation between the energy and the wavelength. I believe I had here the, this is just something which I think it's nice to know, that the 1 centimeter square of ideal black body with the room temperature is emitting 1 photon every 41 seconds. So the intensity of a light emitted by a black body is extremely low. And what you see here is the best black body radiation in the universe. This is a map of the relict radiation, the witness of a black body of the Big Bang, which has been measured. And that is a black body radiation roughly of a temperature which is 2.7 kelvins. Well, it is not uniform, as you can see. And for those of you who are busy with astrophysics or who are interested in astrophysics, that is, that picture is almost a fundamental one when you want to study what had happened to our universe after the Big Bang. All right, so now we know the physics of the electromagnetic radiation, and we know that the visible light is just a part of that radiation. And that picture is, of course, a picture of a contemporary picture of a classical Newton experiment. We have a prism, and the white light is coming from a left, and it splits in different colors. And that permits us to define what is meant by the color we see. If we had a white light, which is, for example, emitted by a sun, then the white light is the mixture of all possible wavelengths of a radiation, a blue, green, and red. And it hits the white object, and that means that all those colors which were in the white beam of light, there's three fundamental colors, red, blue, and green, are passing through it unaffected. So that is why we see the white object. But if all the radiation, which is the white radiation, for example, coming from light, is being absorbed by that body, then is what we call the black object. There are no black objects in the real nature. We might have a very good approximation to the black object, but there is hardly a black object really existing in the nature. And that, for example, is what we mean by the red object. We have a white light which comes, and all the colors except of a red are being totally absorbed. Then the object is red. And sure enough, there is a complete spectrum of possible colors, because there are materials which might absorb a green color, but not absorb a red and blue, and so forth. And therefore, the visual effect we observe are different from those pure colors, for example, shown on this example. That is actually also why do we see the blue light. We have a white sunlight which comes, and when it scatters intensely with the particles which absorb all the other wavelengths except of a blue one, then the sun, we see the skies as being blue. And if there is a lot of dust in the air, then we can see a different color. If you watch the sun setting below the horizon, for example, on a desert, you see that the color of a sun changes when it comes to a horizon. And that is not because the sun is changing, that because the light is coming through a thicker layer of air which contains more dust particles, and therefore it changes the color. Okay. The color perception. The color perception is, of course, a physiological phenomenon. And we shall see in a moment what part of our eye are reacting to what kind of a color. But I would like to point out a phenomenon which is called the after image, which is the one which is used by the painters very often to create desired results. And the after image is the following. If you look at the small area of which is painted with a given color, for example, when it is painted with the, say, red, and you look at this region for something like a 30 to 60 seconds, that is sufficient time for your brain to adjust to the fact that you are seeing a given color for a, and then you rapidly look at the white area. Then all over the sudden, you see that white area being colored. But the color of that white area is not that one which you have been watching for this 30 or 60 seconds, but it is a complementary to the color of the original object. So if you were looking at the red object, as on my drawing, and you will change your view to the white square, you will see the color of the white square being a complementary, which means red, which means green. And if you will be looking at the blue picture and do the same, then you will see the orange color of that white area, and it will fade after a while. And for a period of time, you will all over the sudden see that this complementary color is illuminated more than the original. So that is the phenomenon which is called after image. And there was in Polish language, it's called powidoki. And a few years ago, Andrzej Wajda has shown us his unfortunately last movie called Powidoki, about a very famous Polish painter, Władysław Strzemiński, who had been opposing a social communist domination even in art right after the Second World War in Poland. And that is a movie, is a dramatic movie, which shows what the ideological indoctrination might cause. And but I mentioned that not only because of this title and the story of the Strzemiński, but because there is essentially not seen in the movie hero of that movie. It's the wife of Strzemiński, Katarzyna Kobro. She was a sculptor and also the painter, the artist. She died before him. And as we shall see, Katarzyna Kobro was one of the Polish artists who contribute to the very important manifesto, artistic manifesto, written by the bunch of the painters and artists following a cubism idea in painting. I already mentioned that it has something to do with the use of non-Euclidean geometry. So we will be talking about the Katarzyna Kobro, this unpresent, essentially, person in the movie by Wajda. And there was interesting discussion about it, why Andrzej Wajda decided to make the movie about Strzemiński, about the ideological devastation in culture, without paying too much attention to Katarzyna Kobro, but we will be discussing it later on. And that is the, oh, I'm sorry. Sometimes this is another Van Gogh picture, Le Berceuse, in which Van Gogh uses the after image technique to create the impression. That is particularly on the bottom of the picture. There is a red background, so to say, for that part of a picture, and there is a slightly different than pure green color of the clothes of that lady. And when you look for a longer time on that red square, you will see the after image on the green. This is not so well seen on the computer screens because of the fact that these are not color due to the absorption of the white light on the canvas and the pigment, but the computer screen is illuminated. There is bright light emitted in that area. So this is why it is very difficult to discuss these phenomena showing not the real picture, but something on the computer screen. Since I'm talking about the color conception, let me mention one of the color problems which existed since the mid of the 19th century and which was called the four color problems. The four color problems is a problem if we have an area, two-dimensional area, and we have lots of different regions on it, marked by lines, and we want to color it with the lowest number of possible colors in such a way that no two regions have a common color around the boundary, except that the same color may meet in the one point. And that fourth color problem was proven that the lowest number of the colors you need to paint the surface with the rule I just discussed has been proven mathematically in 1976 by Kenneth Appel and Wolfgang Haken. And that proof is the first proof in mathematics which was obtained on a computer. The Appel and Haken were able to prove that there is a finite number, large number, more than 1,000, of what they call a primitive maps. And then they went on and show that none of those, that the lowest number of colors they need to paint those primitive maps is 4. They didn't need to any other. There was a lot of a discussion whether that kind of a computer proof can be accepted as a proof of a mathematical theorem, but finally that was agreed that this is a correct proof. And this is the illustration of four color problems on some kind of an artist drawing. And that is how the world map looks like painted with the four color rules. And let's continue with the colors. This is what I already have shown you. This is a white light which comes to the blue objects, and that means that the only wavelength which is scattered out of the object is blue. So the other colors are absorbed. And that is how we see a given color. And that is a drawing which shows so-called additive colors. We have the, oh, I'm sorry. I have no idea why this computer is all over the sudden not. If we have two beams of light, red and blue, which are coming to a white object on which there is a single spot in which those two colors are interacting, so to say, with each other, then this spot is having a color which is called magenta. And this explains how the colors are being added. And that is a famous color diagram. We have three fundamental colors, blue, green, and red, in the corners of this triangle. We have a white color, which is in the middle. This is equal amount of a blue, green, and red light mixed together. And we have another triangle with the corners, which are cyan, yellow, and magenta colors. So the colors, we understand how to concept of colors comes in the science, and it was much before we understand that the artists were already using the concept of colors. In the middle of the 19th century, a certain French chemist, Calouste, working for a workshop making gobelins, Les Gobelins actually was the name of that workshop. And he was in the dye department of it, had written a book about the perception and interaction of the light. And that was the first attempt to do the colors, to understand the perception of the colors by from the physical point of view. How do we sense the colors? This is a cut through our eye. And from the viewpoint of colors, the important part is the retina. And retina contains a mixture of cones and rods. And cones are responsible for our reaction to colors, and the rods react to the intensity. And the lens, for example, allows the incoming light to be properly projected on the retina. So, for example, we can pretty well see the boundary between the different colors. A few months ago, I have underwent the surgery of having a lens in one of my eyes replaced due to the cataract developing in the eye, and that is a fantastic achievement of medical sciences, how they do it nowadays. It is a quarter of an hour procedure, completely painless, and next day you see everything. But during the surgery, there is a period of your eyes seeing what is happening, and there is a moment when your original lens is being removed, and then you only see a tremendously different and unseen normally. I never saw it before and after. Colors which are having, it's hard to explain, with not having a boundary. And then when the new lens is being implanted, which is a piece of microsurgery, it is the material is cooled enough, so it is made into a little cylinder, which is inserted by a little hole in the iris, and then under the temperature of your body, it expands to the proper form. then all over the sudden, this mixture of colors, this unusual mixture of colors changes, and all of the sudden you see shadows. First, shadows distinguish different colors, and eventually a sharp boundary. That is the last comment on it, is that it is a very different construction in the human eye than in the other animals. And if you will ever visit Copernicus Science Center, and if you will come there with a child who is below a 6 year of age, then you can go to the children's section. And in the children's section, we have the devices which are fashioned like heads of different animals, a fish, a dog, and a snake. And you can look through by kind of a viewer on the back of that head, and then see the world, how those animals are seeing it. And particularly, I was completely, incredibly, I was flabbergasted by observing how the world is seen by the snakes. They essentially see only those boundaries between different colors. And that is why the tip of the fleet used by those Indians performers who show how the cobras are dancing when they blow the air through that pipe. Well, that is not the music which makes the snakes dancing, because the snakes are deaf, but the tip of that pipe is having colors painted on it. So when the artist blows the pipe, he slightly changes the pipe, and the snake sees this boundary between colors moving, and he adjusts his or her, I have no idea what is the sex of those snakes, changes the head in order to follow the object, not the music. So this is a human eye, and of course the perception of colors by other elements, by other animals, is very different. That is a picture which shows how our cones react to a given wavelength, and that is following the picture from the previous slide. Well, that is another important property of a light. You must have seen it many times. It's called the double slit experiment. There is a source of a light, and we have this double slit, and what we see on the screen is the interference. And even that can be beautifully shown by an artist. This is a fairly recent picture by the Christopher Dean, which is called Red Dinah. And that is the interference shown with the proper colors on it. And it's a kind of a color play by that artist. And I would like to finish today's lecture with that particular picture and discuss it a little bit. This is called the Lightning Express, Leaving the Junction. It is this is a color metallographic picture made by Curie and Ives in 1863. these two gentlemen were those who had brought the art to the living quarters of an average American, so to say. They were able to produce by metallography paintings, copies of various paintings, or making the paintings by themselves, which were affordable for many people. So in the turn of in the second half of the 19th century and on the turn of a century, the essential feature in the living rooms of relatively well-to-do Americans were the paintings made by that pair of the artist. And why I am showing that picture, and I will show it again and again, is that it had shown two things: the fascination of the artist with the civilization change, which had happened roughly at the time, when the communication becomes almost instantaneous as compared to what was before. The railroads have changed the way how the concept of time had entered the human life. Before the travel by trains, the concept of time was very local. People were having a one watch on the church or tower. For years, the clocks there have only one arm. There was not even the need to distinguish half an hour or so. But if they were traveling, the travel was so slow that the geographic change of the time zones was not having any influence. The same was in the travel by sea. It was pretty fast already, but as compared to, I mean, the ancient times, but in any case, it was sufficiently slow that the notion like a jet lag, for example, was completely unknown. But when the railroads become common, the question of a time becomes a problem. And we shall see how that had influenced the art and how it also influenced the science. So I think it's time to break. And thank you. How do I stop sharing it? And yes, it's gone. Oh, recording had stopped. I didn't know that by stop. Anyway, we see each other next.